Welcome back, scholars. Today, we're going to build upon our knowledge of matrix operations with a few concepts and skills. To get started, let's talk briefly about a special matrix referred to as an identity matrix. Now, an identity matrix can be very easy to spot because its entries consist entirely of ones and zeros. However, the arrangement has some additional requirements. We usually refer to an identity matrix using a capital and italic I. The identity matrix is always a square matrix, but it does not have to be a 2 by 2 or a 3 by 3 specifically. It can be any n by n matrix. As I mentioned, every entry is a 1 or a 0. However, the ones appear specifically along what is referred to as the main diagonal. So here's a 3 by 3 identity matrix. As you can see from the top left corner down to the bottom right, we have a diagonal arrangement of ones. The main diagonal for any matrix will run from the top left down to the ground floor, or the bottom row of that matrix. So the identity matrix looks interesting, but what is it useful for? Well, as we'll see in a moment, this is the matrix equivalent of a 1 in real number multiplication. For example, if we multiply any real number by 1, we get the number itself. Let's take a look at what happens when I multiply a matrix by an appropriately sized identity matrix. Remember that when multiplying matrices, we go row by column. So we'll start with the top row, first column. That'll be A times 1 and B times 0. Then top row, second column, A times 0 and B times 1. Next, we'll go bottom row, first column. That'll be C times 1 and D times 0. Last, we have bottom row, second column, C times 0 and D times 1. Now, let's look at the sum of all of our products for each entry. That's just going to be A, B, C, and D. So in other words, we get our original matrix, A. All right, let's test and see what the product will be for I times A. As we saw previously, matrix multiplication in general is not commutative. Go ahead and pause the video and practice multiplying here. Did you end up with A, B, C, D again? Interesting, so it seems like matrix multiplication is commutative in this specific circumstance. I wonder what happens if we use something like an identity matrix, but instead of using ones along the main diagonal, we have -1. Go ahead and pause the video and multiply, then we'll check back and see what we find. Okay, interesting. It looks like the magnitude of our values A, B, C, and D remain unchanged, but the sign will be the opposite of the original value. This is actually an example of a transformation matrix. If you imagine row 1 represents an x coordinate in an ordered pair, and row 2 represents a corresponding y coordinate, then the -1 in the top row means that we will reflect over the y-axis, say from quadrant 1 to quadrant 2. And the -1 in the bottom row means that we will reflect that y-coordinate over the x-axis, say from quadrant 2 to quadrant 3. This corresponds geometrically to a 180-degree rotation. So let's summarize what we've learned. The identity matrix I is a square matrix with ones on the main diagonal. Otherwise, all the entries are zeros. We've also shown that the product A times I equals the product I times A, which equals A itself. Next up, we're going to quickly describe what it means to transpose a matrix. We saw previously that we can represent real-world data using a matrix. The example that we looked at were grade weights for various grades for multiple students. We also saw that matrix multiplication requires specific dimensions in order to be a defined operation between two matrices. In some cases, it may be useful to swap the values of our rows and columns. To do this, start by finding the main diagonal. Again, that's going to run from the top left corner across to the ground floor or the bottom row. Then we're going to swing that top row down to make column 1. Then we'll swing around row 2 to form column 2. You'll know you did this correctly if the main diagonal in the transpose matrix remains unchanged. We can see the entry 6 and -9 in our example as well as in the transpose matrix. So it's a thumbs up, we did it right. A couple of more key points here. A superscript, that's like an exponent, capital T, is used to represent a transposed matrix. You'll see this as a button or an option in popular matrix calculators like Desmos. It's also true that if you take a transpose of a transposed matrix, you're back to the original matrix. Again, this technique has many uses, but it's often particularly useful if you wish to multiply matrices that have incompatible dimensions. The last topic we'll look at today is the so-called determinant of a matrix. We will rely on this calculation in future discussions, namely finding the inverse of a given matrix. But for today, we'll focus solely on calculating the determinant. In general, the notation used to represent the determinant resembles that used for the absolute value of a real number or the magnitude of a vector. We see these vertical bars positioned around the capital letter naming the matrix we are finding the determinant of. When you see this notation, it means the determinant of matrix A. You may also see this shorthand notation DET for determinant of matrix A in textbooks, websites, on calculators, or in software. Another very important point, we can only find the determinant of a square matrix. So like the identity matrix, today we're focused only on square matrices. We'll start by finding the determinant of a 2x2 matrix. We use letters as placeholders for each entry. So we have A, B, C, and D. The determinant will be a single value, which will be the difference between two products, A times D and B times C. To visualize this, I've drawn arrows indicating the products. The blue will be the first product, and the red will be the second product, which we subtract. We'll practice with matrix B. We have 6 times 4 minus 8 times 3. That will be 24 minus 24, or simplified, just 0. Notice in the notes here, we see that if the determinant of a matrix is 0, then its inverse does not exist. So we just found that the determinant of matrix B is 0. Therefore, we know that the inverse of B, denoted with that superscript, -1, does not exist. Again, we haven't studied inverses yet, but we are working our way in that direction shortly. All right, let's see what happens when we want the determinant of a 3x3 matrix. This time, the calculation gets a little bit more involved. To help visualize the products, I've color-coded some things here. Before we calculate, let's observe the pattern of what is happening. We start with the top row, A in blue, B in green, and C in red. Now, we are using A, B, and C as a scalar multiple of the determinant for each of 3 2x2 matrices. Next, let's look at the parentheses. You'll notice the pattern resembles finding the determinant of a 2x2 matrix. So essentially, we have A times the determinant of a 2x2 matrix, highlighted in blue here, then B times the determinant of the 2x2 matrix formed by the two green regions. Last, we have C multiplied by the determinant of the 2x2 matrix formed in the red region. While I'm sure you'll agree that the actual calculation is not difficult, the process overall is very detail-oriented, so we'll want to be careful here. Let's practice by finding the determinant of matrix C. Let's fill in our A, B, and C scalars first. Now let's work with the products paired with scalar A, what we color-coded blue. That will be -1 times 4 and 0 times 1. Next, we'll move over to green or scalar B. This will be 0 times 4 and 0 times 2. Last, we'll move over to red or scalar C. This will be 0 times 1 and -1 times 2. Finally, we'll simplify everything, and it looks like we'll end up with a final result of -2. The last question asks if the inverse of matrix C exists. Well, since the determinant is not 0, we know that yes, the inverse does exist. And in our next lesson, we'll look at how to calculate that inverse.